All right, everybody. In this video, we are going to introduce a new kind of vector-valued function, and this is the vector field. Now we have a relatively straightforward definition, at least on the surface. A vector field on n-dimensional space is going to be a function and a vector-valued function, f, from Rn to Rn. All right, and that is our whole definition. Now, I have a couple things to point out here. The first is that the core point of the vector field, or I should say what makes a vector field, is that the input space and the output space are the same dimension. So the domain and the codomain are both n-dimensional space in this case. It is a vector-valued function, by which I mean that the output space is n-dimensional, where n is bigger than 1. And so the output space can be visualized as a vector. And maybe a better way to say that is that for any given input, the output can be visualized as a vector. But with a vector field, we are often going to adopt a really particular interpretation in which the domain space, so the n-dimensional space that we're plugging into our function, is going to be usually visualized as points in Rn. So these are going to be the points in Rn that we plug in, while the output space, so the same n-dimensional space, or the space of the same dimension, this will often be visualized as the outputs being vectors in Rn. And I'll talk about why we do this and what precisely this means down below. The final thing that I want to say is that because this is a vector-valued function, we often have the function with our little arrow on top, so that's our arrow, and it is often convention in our vector fields that we use a capital letter to represent the function. So most of the time, a vector field, oh, didn't mean for that to happen, there we go. Most of the time, our vector fields will use a capital F, a capital G, and so on, as opposed to our other functions that we've seen, or for example, a path, where we use a lowercase function letter f. All right, so with that, let's get into what a vector field might look like. I have two examples that I want to explore today. The first is a constant vector field, by which I mean that the output is a constant expression. It doesn't depend on x or y. And so this is the constant vector field function, f of xy equals 1, 2. Now, notice we are emphasizing or re-emphasizing that the input is this point, x, y, while the output is this vector, the vector 1, 2. So we see that emphasis here as well. Now, the way that I often interpret a vector field is visually. Vector fields are very visual, very geometric objects. And so here is what I will often do. As I want to interpret my vector field, I'll perhaps, using technology or on a sheet of paper, run a small series of calculations. So I'll plot, or I'll calculate our vector field at a couple different points. And it doesn't really matter. I'll usually create some sort of grid or some sort of lattice. I'm just going to write a few of these down because the pattern will become pretty clear pretty quickly. Okay, and so these might be a number of points that I try to plug into my vector field in order to calculate what the output is. So in this case, I'm plotting 5 different points. Now, because this is a constant function, the results are all going to be the same. And in particular, no matter what my x and y are, the output is always 1, 2 in this example. So f of 0, 0 will be 1, 2, f of 1, 0 will be 1, 2, and so on, and so on, and so on. We'll see that all of these outputs are 1, 2. But the real question is, how do we interpret this on our graph? Well, what I'm going to do is often draw my vector field, and I'll draw each point, or I should say, I will draw each of the expressions I've computed here in the following manner. So I'm going to focus on 0, 0 first. The fact that f of 0, 0 is equal to 1, 2, I will interpret that by marking the input value as the point. So there's my point 0, 0, and then attached to that point is going to be the vector 1, 2. So in this case, 1 over, and whoops, I'm drawing the wrong vector. Not 2, 1, but rather 1, 2. So 1 over and 2 up. So we should get this as our output. Now again, this is a function with a two-dimensional input and a two-dimensional output, but I am interpreting both input and output on the same picture by marking the input as a point and the output as a vector attached to that point. And so let's do the next one equally carefully. We'll plug in the point 1, 0. So that will be this point right here. And its output is the vector 1, 2. Now, the vector 1, 2 is the same vector we've already drawn, but vectors can be attached or anchored to any initial point, not just the origin. So I will draw the vector 1, 2 anchored at my input value. And so that input and output pair will be represented by this second arrow anchored at this new point. And so we can proceed, and I'll just plot. We have our point 2, 0, we have our point 0, 1, we have our point 1, 1. Those are the 5 that we've explicitly drawn here. And you'll note that for each of these, our output is a vector 1, 2. So we get an expression that looks like this. And because these are just 5 points, of course, this is not the complete picture, but you can imagine to get a complete idea of what our vector field looks like, we could end up drawing a whole bunch of arrows indicating the behavior of our function. And here I've just drawn a number of these. There's no set number that you are supposed to draw or anything like that. Of course, our input space, we have infinitely many points in the plane, so we're not going to draw them all, but you draw enough to get a general sense of the vector field. Here, each of the points we've plugged in has the output vector of 1, 2, and so all of these vectors are the same vectors anchored at different input points. Okay, and that is our main interpretation of our vector field. We interpret it in this way because a vector field is often being used to describe a larger kind of motion that might be occurring. This is often how it occurs in classes like physics or maybe chemistry, where you're describing a fluid flow or a gas flow or some kind of movement that's occurring. What you're describing is at each point what the current flow or what the current direction of movement is. All right, so with that, let's take a look at this second example. This is g of xy equals, and now this is not a constant vector anymore, or a constant vector field. We have g of xy equals xy. And so I'll just make a few notes here. I think it will be really clear what the pattern is. G of 0, 0, we're going to plug in and get 0, 0. So of course, plugging in for x and y, we're getting x equals 0, y equals 0. We've also got g of 1, 0 is 1, 0. G of 0, 1 is 0, 1. G of 1, 1 is 1, 1. And I'll stop plugging in there. You clearly get the idea. As I go to draw these, let's take a look. So I'll actually start with the second one. Let's start with g of 1, 0. 1, 0 is the point right here. And so g of 1, 0 is the vector 1, 0. And so that moves 1 in the x direction, 0 in the y direction. And so that is our point there. G of 0, 1. So this is the point 0, 1. and the vector 0, 1 goes 1 unit up in the y direction. This is now a non-constant vector field because our vectors are not all the same. They're differing from point to point. Oops. And so we also see if we plug in the point 1, 1, we'll get the vector 1, 1, and so we'll get something that looks like this. Now notice if I try to plug in the vector or the point 0, 0, I get the vector 0, 0. That's the 0 vector. This is allowed, but I cannot draw the 0 vector with any magnitude and direction, so I'll just leave that point as it is here, just a point. And now if I wanted to draw many more points, you can see a pattern. So here's 0, -1. Here's -1, -1. And as I draw these points, we start to notice that our vectors are all pointing away from the origin. And that is the shape that this vector field takes. Now, I'll point out that if we're not careful, our vector field can get really messy. This already began to happen in our last image, where the vectors all got really close to each other. But notice how challenging it can be here if we plot just a few more points. So if I plot the point, this is the point 2, 1, the vector will be the vector 2, 1. And if I plot the point 2, 2, the vector will be the vector 2, 2. And if I wanted to plot the point, let's say 3, 3, the vector would be the vector 3, 3. So that has to go 3 over and 3 up from the location I'm currently at. And so we begin to see that these vectors have the potential to start overlapping and to cross themselves. Not cross themselves, but maybe rather cross each other, lay on top of each other, what have you. And this will just get worse as we go further away from the vector, from the origin, because for this vector field, the further away we are from the origin, the larger our vectors seem to be. And so this can quickly become really hard to look at. And so there's a convention when creating a vector field to often draw the arrows, but to not draw them completely to scale, to make them a little bit shorter than they would be otherwise. And in doing so, to keep the picture just a little bit neater. So I might draw, if I were trying to display this to a class, let's say, I might start drawing my vectors kind of like this. What I'm trying to do here is I'm trying to indicate that the vectors are pointing away from the origin and that they get a little bit longer as I go further up. But everything has been scaled back a little bit just to keep the picture a little bit cleaner and to keep these vectors from crossing each other. So that is also a trick that we will employ, especially when drawing these by hand. If we use technology, that will often happen automatically. And so for more complicated vector fields, technology is often the way to go. The final thing that I want to say, this is a more advanced topic and outside of really the scope of a Calc 3 class, but to put it in the back of your mind for a future class, I want to mention the word field here. The word field is a word that's used in several different ways in mathematics. For example, in abstract algebra, a field is a kind of algebraic structure. But here in Calc 3, the fact that we're using the word field has a very particular connotation, distinct from the abstract algebra connotation. So in Calc 3 and in classes that are similar to Calc 3, a field can mean that at each point in the domain, we assign a kind of object. So at each point, we assign an object. Because this is a vector field, that means that at each point in our domain, we are assigning a vector. And you see that's exactly what we've been doing. We've been looking at each point And at each point, we're anchoring a vector. But you can imagine as we get other kinds of geometric objects, I shouldn't even say geometric objects, as we get other kinds of mathematical objects, you could imagine a field that assigns that kind of object to each point. As a really, I'll give two very brief examples of this. One, which is maybe almost too, what's the word I'm looking for? One that is overcomplicating a simple idea is what we might call a scalar field. So a scalar field says at each point in the domain, we could assign a scalar number. And I say this is complicating a simple idea because the points in the domain might just be something like x and y, a point in the plane, for example. And if I'm assigning a scalar to each point, that can be a function that takes in an x, y, and outputs a scalar number, for example, just some real number z. So a scalar field is just an overly complicated way to say that it's just a standard function from Rn into R1. The scalar aspect is that R1 on the output, and the fact that it's a field is saying we're assigning to each point in our domain, our Rn domain, this scalar number from R1. So that is an overly complicated way to say, to discuss an object we've been talking about all semester. You can create other kinds of objects out of a field, or I should say you can create a field out of other kinds of objects. And so you could imagine, for example, I'll call it a matrix field that assigns a different matrix to each point, or more advanced concepts that we won't be covering in this class, but an important mathematical object in higher mathematics is something called a tensor. A tensor can be thought of as a more advanced kind of matrix. And tensor fields abound in the fields of higher mathematics, and especially any sort of analytic geometry. So this language of field comes up again and again, and vector fields are kind of our first introduction to it. So a little bit of an aside to end the video, but I thought it was a nice note. That will do it for now. Thank you so much, and see you next time.